go ahead and get at this. This section is on, so the title is Shifting, Reflecting, and Stretching Graphs. So we're going to go through what we could call parent graphs or a library of functions, a library of graphs. These are kind of the basic building blocks, some of the things that we definitely want to understand about basic graphing and stuff like that. You've probably seen several of these before. We want to make sure that we're familiar with the shapes that these create. And even though we used the calculator the last couple days, and you know how to throw these into a calculator and have it graph them and pick an appropriate window and stuff like that, listen very carefully. That is not the point. The point is not that you can get a picture of what it looks like on the calculator. The point would be, do you understand why it makes the shape that it makes? Okay? Because the better fundamental understanding you have about the basic shape of a particular function, the better off you are in understanding what happens when we transform that shape and what to expect. Because remember, one of the things that we said when we were using the calculator is you should know roughly or have some ballpark idea of what the calculator is going to give you when you type something in, whether it's a graph or an expression or something like that. Okay? So here's what we want to keep in mind. Every function makes a shape when we graph it. And that shape is a picture of all the points that work in the equation or that make the equation true. So if we pick a point that's on the graph, it should work in the equation. It should make the equation true. And if a point makes the equation true, that's why it's on that particular graph. Okay? So there are several shapes and several functions that we work with all the time. And we're going to go through, hopefully these are some relatively easy ones that you're familiar with. Okay? But you want to think about why it makes the shape that it does. So the first one that we're going to go over, and we'll use these names, this is called the constant function. Okay, and you'll notice we have what looks like a variable right here. Okay, so f of x equals c. Okay, I may have mentioned this before, but remember, letters at the end of the alphabet are usually used to represent variables, and letters at the beginning of the alphabet are usually used to represent constants. Okay, so this would be like f of x equals a particular number. So let's do a particular number. Let's do f of x equals 2. Now remember, y is the same as f of x, so if I wanted to, I could write this function this way, y equals 2. And what shape does that make? Horizontal line, okay? And the reason they call this a constant function is okay, because y is always 2 because y is constantly 2, okay? Another reason would be it doesn't increase and it doesn't decrease as we go from left to right. It's always constant. It's always 2, okay? So the domain for a constant function is all reals or from negative infinity to infinity. Okay, you can plug anything you want in there because there's no division, there's no even roots, and there's no logarithms or anything like that. No issues like that. And what's the range? In this particular case, it's 2, but let's say in general, it would just be whatever the constant is. Because if we squish this onto the x-axis, so if I were to squish this onto the x-axis, it would come down here, cover the entire x-axis. If we squished it onto the y-axis, it would only cover 2. That would be it, okay? Or whatever the constant happens to be. Any questions there? Okay, this is called the identity function. Okay, and it would be the same as writing y equals x, which we know is a line that has a slope of 1 and a y-intercept of 0. So it looks something like this. Okay, now for this one, we're going to take just a second and we're going to think about what would be the points on this graph and why are they these particular points. It goes through 0, 0 because when I plug in a 0 for x, I get out a 0 for y. Okay, the x and the y coordinates are exactly the same. So from that center point, if you want to think of it that way, when I plug in a 1, I get out a 1. Plug in a 2, get out a 2. Okay, when I plug in a negative 3, I get out a negative 3. So the coordinates are both positive here. The coordinates are both negative here. So I get this nice perfect 45 line that goes through the origin. Okay, what's the domain? All reals, negative infinity to infinity. What's the range? Okay, we get answers way down here, all the way to up there, okay, as far as you want to go in either of those directions. So the domain and the range are from negative infinity to infinity. Okay, let's take a look at, so that's, again, so if I say the identity function, that's what we're talking about. We're talking about y equals x. Okay, and let's talk about x squared. Again, something that we're probably all very familiar with. If we plug in a 0, we're going to get out a 0. So it goes through 0, 0. If you plug in a 1, you get 1 squared. So that's 1. If you plug in a 2, you get 2 squared. So that's 4. Plug in a 3, that's 3 squared, so that would be 9. That would be way up here. Okay, now if you just looked at a couple of these points, let's say we only did these first 3 right here, it's pretty clear if you do an accurate graph, there's no way this can be a line. Okay? And then if we plug in -1, what happens when we square a negative? Turns out to be positive, so we end up with a +1 here. If we go back to -2, we end up with +4 again. And we end up with this curved shape right here that has a special name. Now, not everything that's curved like this or looks close to this is called a parabola or the square function. This is the square function because whatever the x-coordinate is you plug in, you square it to get the y-coordinate. Okay, so I've got a question for you. Why does this one go up on both sides and this one goes up over here and down on this side? Why is this one in quadrant 1 here and quadrant 3 here, and this one's in quadrant 1 and quadrant 2? Hop. Yeah. When you square a number, it's going to turn out to be positive. So when I plug in negatives, instead of getting negative answers like I did here, I end up with positive answers. Okay? And why does this curve rather than go straight like this one does? That might be a little tougher question. Why does this one curve like it does rather than go straight like that one does? Lynn? Okay. Better way to say it would be, it's got an exponent, so we call this a power. Okay. When you plug in a 3 here, you multiply the 3 by 1, basically. When you plug in a 3 here, you multiply it by itself. You multiply it by 3. When you plug in a 4, it gets multiplied by 4. So every number gets multiplied by itself. That creates a much steeper graph. Okay. Let's talk about the domain and the range. What can you plug in? Anything you want, from -infinity to infinity. What do you get out, though? Okay, you get 0 to infinity. You only get positive numbers out, or let's be a little bit careful about this and a little bit more specific. Jordan, what type of bracket do I put on here, a round or a square? Definitely going to be square here, okay? All these answers, when we square something, we get an answer that is non-negative, okay? So 0 or positive, okay? Remember that vocabulary? Okay, and let's take a look at the next one. This is the cubing function, okay? So let's think about what cubing would do. When you plug in a 0, you get out a 0. When you plug in a 1, you get out a 1. Take a look at that. These have exactly the same points right here, but let's plug in the next one. Plug in a 2. 2 cubed. 2 times 2 times 2 again. So what's the answer here? 8. So we're at 2, 8. Let's plug in a -1. -1 cubed is, how many negatives? 3. So are we going to have a positive or negative answer? Negative answer here, okay? Plug in a -2. We're going to get out a -8. So here's what the graph looks like. Okay, everybody watch, please. Is that part of a parabola? How many say yes, what I just drew there is part of a parabola? Okay? And how many say no, it's not? Okay. The minority's winning most of the time here. It is not. That is not part of a parabola. It kind of looks like this shape over here, but it is very, very different. Okay? Logan, you said it's not. Can you help explain why it's not? Okay, I'll take that. It's steeper. That's a good way to say it. When we plug something in here, we only multiply it by itself once. We square it, and that makes this specific shape called a parabola. If you're cubing, even if you just look on one side, it makes a shape that's completely different. When we plug in a 2, we get out a 2 times a 2 times a 2. We get out an 8, much, much steeper. And if I were to plug in a 3, it's going to be 3 times 3 times 3. It's going to be 27. One heck of a lot bigger than this right here. okay? And the slopes between each pair of points get steeper and steeper and steeper in a much quicker fashion than they do over here, okay? So even looking at one side of this, it's not part of a parabola. And you can tell the whole thing's not a parabola because on the other side, it goes down like this, okay? Now, let me show you one more thing, or talk about one more thing that would be important here, okay? That when you start studying stuff in Math 1050 and in calculus, these things are important, okay? This one right here is definitely steeper here. It's also flatter in here. So it's actually steeper on the outside of one, and then in between -1 and 1, it gets pretty darn flat. It's a lot flatter than this nice gentle curve for a parabola, okay? I haven't drawn that very well, but that is what happens, okay? Domain, all reals, right? -infinity to infinity. Range, same thing, -infinity to infinity, okay? Look at the similarities between the two of these. Starts down here, ends up here. Starts down here, ends up here. You can plug in anything you want and get out any number you want. So the domain and range for both of those are from -infinity to infinity. Any questions there? Okay, let's take a look at two more graphs that are used quite often. Let's talk about the square root function. This is the first one that we've come across where we have a domain issue. Let's do that first. What numbers are we allowed to plug into the square root function? Positives. And 0. So the domain is going to be 0 to infinity, including 0. Okay, so let's start by plugging in a 0. Square root of 0 is 0. Totally okay with that. Plug in a 1. Square root of 1 is 1. Okay, now let me stop and pause right there for just a second. Take a look at that. Haven't nearly every one of these, in fact, of the 4 graphs on here, or the 4 graphs previous, didn't all of them go through 1, 1? Or sorry, those 3 did. They all did, right? Okay, but again, each one of these functions makes a completely different shape. So let's plug in, oops, let me make that a little bit bigger. Hopefully that'll stick around. Let's plug in a 2. Is that a good number to plug in here? Nope. You'd have to know roughly what radical 2 was. Okay, it's about 1.4, so we could graph 1.4. I'm not going to, but it would be about right there. Plug in a 3. Radical 3 doesn't have a nice square root. What is the next most convenient point to plug in? A 4, because 4 is a perfect square. Okay, so if I plug in a 4, I get the square root of 4, which is a 2. After 4, what's the next most convenient point to plug in? 9, because the square root of 9 is 3. So if I go out here to 9, I get a 3. And here's what the graph looks like. So what's the range? What type of answers do we get out? We get 0 to infinity. This continues going up and out. Okay. Take a good look at this. Does this have anything to do with any of the shapes that we've got up here already? Does this pattern look somewhat familiar? Yeah, Raymond. It's a sideways parabola. Okay. Does it fit that pattern? So I want you to notice this, and this is important, so please watch. If you haven't thought about parabolas like this, please include this in your thinking. Okay, this point right here is called a vertex. Okay, so we've got this point 0, 0, and then this point is 1, 1. So from that little turning point, if you will, okay, we go over 1 and up 1. This point right here is 2, 4. So back from the vertex, back from that turning point there, we go over 2 and up 2 squared, so we go up 4. Well, take a look at this right here. If I go up 1, I go to the right 1. If I go up 2, I go to the right. How far to get to this point right here? I go 4. Okay, so let me write these points down. This was 0, 0. Okay, this one was 1, 1, and this one was 4, 2. So this is a top half of a sideways opening parabola. Okay, and we'll study the relationships between these. You may already know how the two of those are related. Okay, we use square roots and squares all the time. In fact, we use them to undo each other, don't we? Okay, so there's definitely got to be some sort of relationship there. Okay, now we could go through each one of these and we could label these points. Hopefully you've got an idea. So if I point to this one right here, what is that point again? 2 comma 8. What is this one right here? Negative 1, negative 1. How about this one right here? Negative 2 comma negative 8. We actually looked at this one before. We've had this in part of our lessons. This has a name. Besides the cubing function, it falls into a category of functions. What type of function is this? Because of its symmetry. I see some people going, yeah, it is odd. This is an odd function. It's symmetric with the origin. Okay, it's an odd function. Okay, what about this one? This is even. Okay, it's symmetric with the y-axis. Okay, any wonder why they chose those to be the names of functions that are symmetric with the origin here and the y-axis here? Okay, good reason why they chose those. Okay, and then let's take a look at the last one, the absolute value function. Before we graph this, has anybody seen this before, and can anybody describe what shape this makes? What shape does the absolute value function make, Raymond? It makes a V shape, okay? And let's talk about why it makes that V shape. So if we were to graph this, if we plug in a 0, the absolute value of 0 is 0. If I plug in a 1, the absolute value of 1 is 1. Plug in a 2, it's a 2. Plug in a 3, it's a 3. So we get something that looks like this. But what if we plug in a negative 1? Absolute value of negative 1 is positive 1. Absolute value of negative 2 is positive 2. So we get this nice V shape, perfect 45-degree angle coming in and perfect 45-degree angle going out. Or another way to think of this, and this might be important later on, maybe you've seen this before, this is like the line y equals x. This is like the line y equals negative x. So if you plug in an x on the positive side, you get exactly what you plugged in. What if you plug in an x on the negative side? Say I plugged in negative 3. Plug in a negative 3. Negative negative 3 is positive 3. So what we have here, watch carefully, we have two different functions that would represent the absolute value. It looks like negative x if x is less than 0, and it looks like positive x if x is greater than or equal to 0. We could actually use a piecewise function to describe the absolute value graph, because it's definitely got two pieces here. We've got this graph that's going up and this graph that's going down, and they come to this point, this vertex point. Okay? Domain. Anything you want, right? Negative infinity to infinity. What about the range? Non-negatives, or from 0 to infinity. Okay? Any questions? Okay, so the great part is, once you know what these shapes are, and these should be committed to memory. Like if I point to this right here, you should know that that's the point 3 comma 3. If we come up here and point to something simple like this, you should know that that's the point negative 2 comma negative 2. And that all of these have the exact same y coordinate. In this particular case, it's 2. So you should know and be able to figure out really quickly what each one of these coordinates are for these points. Okay, so you know these basic shapes. Okay, again, sometimes we'll call these parent graphs. Okay, well, once you know the pattern and the shape produced by a particular function, you can take the graph and you can move it up or down. You can move it right or left. You can stretch it or you can shrink it. And if that's not a vocabulary that you're familiar with, hopefully by the time you are familiar with that, okay, and you can even do something called a reflection, which we're a little bit familiar with. We can reflect that across the x-axis. We normally don't reflect them across the y-axis, but we'll do just a little bit of that. Okay? And all of those functions, all of those changes make a new function. And we call those changes a transformation. So if somebody says, hey, we're going to do a transformation of a function, it's nothing scary. All we're going to do is we're going to take one of those basic shapes and we're going to stretch it and shrink it, move it left, right, up, down, or something like that. Okay? And I'm hoping this is stuff that most of you have seen before, because what we're going to do here is we're going to take the basic shape of x squared, the squaring function, that basic old parabola, and we're going to do this with it. We're going to subtract 2 from it, and then we're going to subtract 2 from the x and then square, and we're going to take a good look here. So if I take this one right here, okay, this is that regular old parabola. Okay, it looks like this. Goes through 0, 0, that's where the vertex is. I go over 1, I go up 1 squared, over 2, up 2 squared, so up 4, back 1, up 1 squared, back 2, up 2 squared, and I get a shape that looks something like this. Okay? That's the regular old shape. What does the minus 2 do to this graph? It moves it down 2, okay? Because what we're going to do is, and I need you to think about it this way, so is everybody paying attention? When I plug in a number, let's say I plug in a 0, the first thing that happens is I square, and that makes a shape on this, or a point on this shape right here. Then I'm going to subtract 2 from it. So what I get out is a negative 2. When I plug in a 1, I square it, it makes a point on this shape right here. Then I take that y coordinate and I subtract 2 from it. So I go down 2, and I'm right here. Plug in a 2, make a shape on this graph, and then move it down 2 units. So that's going to put a point right here. So if you'll notice, everybody watching, see these 5 blue points right here? From the vertex right here, from this turning point, if I go over 1, I go up 1 squared. If I go over 2, I go up 2 squared. So I'm going to go up 4, and look, I land right there. Same thing on the other side. If I go back 1, I go up 1 squared. If I go back 2, I go up 2 squared. So I get this shape right here. It's the exact same shape, it's just been shifted down, vertically shifted 2 units down. So if I take a function and I add k, again, toward the beginning of the alphabet, that's going to be a constant. If I add something or subtract something after the function's made the shape, it's going to take the pattern and it's going to move it up or down based on whether we're adding something or subtracting something. Okay, and we call that a vertical shift. Let's take a look at this one right here. Again, here's what the parent graph looks like. Here are those, we'll call these 5 key points on the original one. Let's think about what happens here, okay, and contrast it between the 2 of these. When I plug in a number here, the first thing I do is I square it. That makes a shape on this original parabola. Then I take whatever value I got out and I subtract 2. Something completely different happens here. What happens here when I plug in a number? Let's say we plug in a 0. Brandon, what happens? Okay, it is going to move it to the right 2. And here's what happens. When I plug in a 0, I get negative 2, then I square it. And what do you get when you square negative 2? Positive 4. So I plugged in a 0, I got out a 4. Let's plug in a 1. If I plug in a 1, the very first thing I do with it is I subtract 2 from it. So that's negative 1. Then I square it. Squaring is what makes the shape. So that would be negative 1 squared, so I get 1. What happens when I plug in a 2? The very first thing I do is what? Do I square or subtract? I subtract. I subtract 2 from the x that I plugged in, so I'm changing the x, then I square. So if I square 2 minus 2, that's 0 squared, so I get a 0. And then if I plug in a 3, 3 minus 2 is 1. Square that, I get a 1. And notice what we've got right here. I get these 5 points, which I'm going to connect. And again, notice the pattern. Here's the vertex. If I go over 1, I can go up 1 squared, and I'm at a point on the graph. If I go over 2, I can go up 2 squared, and I'm at a point on the graph. What is this point, by the way? What would its coordinates be? If this point right here was moved over 2, so we're at 2, 0, what's this point right here? I went over 2, so that would be 4, and how far up did I go up? I went up 4. Okay? Let's do this one right here. Again, that one would have been 1, comma 1, and this would be 0, comma 4. Again, notice that exact same shape again. This one's going to be 3, 1. It's that same parabolic pattern. It's that same growth pattern from that vertex, over 1, up 1 squared, over 2, up 2 squared. Okay? And could we label these right here? 2, 2, 1, -1, 0, -2, and then you could label the points on the other side as well, right? Any questions? Okay, so Brandon said it moves it to the right 2 units. So let's take a look at what would happen if we wrote this down in general. Notice the difference between the two of these. Here we make the shape, then we add or subtract a number. What's happening right here? What's the first thing that happens here? Add or subtract something from the x. So it should make sense that if we add or subtract something from the x, we're going to move it in the x direction. So if we add something, well, let's do this one. If we subtracted, which way did it move it? It moves it to the right. And if we add something, it's going to move it to the left, and we call this a horizontal shift. Okay, so let's take a look at a couple of others. If I plug in a 0, I get a 0. If I plug in a 1, square it, that gives us a 1, and what's in front of that? A negative. So it would be -1. Plug in a 2, square that, we get a 4. There's a negative in front, so we get -4. So what is this doing to our parabola? Okay, so this is doing what we'll call a vertical flip. Okay, so it's being vertical flipped, or it's a reflection across the x-axis. Multiplying that by a negative out in front here, there's our function. There's our squaring function that makes the parabola shape. Multiplying it by a negative flips it upside down. Okay? Any questions there? Reflects it across the x-axis. Okay, let's take a look at these two guys right here. Plug in a number, like 0. We get 0, and then times it by 2. You still get 0. When you plug in a 1, square 1, times it by 2. We get out a 2. Plug in a 2, square that. We get 4, times by 2, we get 8. So this is going to be, let's see, we're way up here. So this is 2, 8. This is 1, 2. And this is 0, 0. And what happens on the other side? What happens if you plug in a -1? I hear people saying, what is it? It's the same thing, right? So this is going to be a 2 here, and this is going to be -2, 8. And this is -1, 2. And we get that shape right there. Okay, even though this has the point 28 on it, is this part right here, is that like a cubing function? Nope, it's not. Okay, even though it's got that point 28, it's not part of the cubing function. Okay, definitely not, because it goes up on both sides here. Okay, and what's happened here is it's important to think about where this came from. The original graph looks like this. Goes through these points. Does it look like each one of these points was made twice as tall? Okay. So what we call that is, we call that a vertical, in this case we call it a vertical stretch. We took the points, and everybody watch please. Okay, watch. Okay, some people will look at this and they'll say it did this. Okay, it made it narrower, made it skinnier. Okay, that's not the right way to think of it. What happened was it took all the points and it made them taller, made them twice as tall. It changed the y-coordinate, okay? The y-coordinate here used to be 1. We doubled it. It's now 2. The y-coordinate at this point used to be 4. We doubled it, so it's now 8. We doubled the y-coordinates. We changed this in a vertical direction. We call that a vertical stretch. Or this one here is going to be a shrink. It's a stretch if a is greater than 1. It's going to be a shrink if that number sitting out in front is between 0 and 1. Okay? So we're going to graph this one right here. We're going to graph this vertical shrink. And it's got a fraction in it, so maybe that's not our favorite. But here's what we'll do. I'm going to graph the original one. The original one goes through these points right here. 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. So if you plug in a number, you get an answer on this graph right here, and then what do you do with it? Plug in a 2. What do you get? 4, when you square it to make this shape right here, and then you multiply that answer by 1/4. So we're not going to graph 2, 4, we're going to graph 2, 1. You plug in a 1. You get a 1. You get this shape right here. If you multiply that 1 by 1/4, you get 1/4. What happens if you plug in a 0? You get 0. And if you plug in negative 1, you get a 1/4. And if you plug in negative 2, you get 1. So you get a graph that looks something like this. And again, let's make an important distinction. Okay, look up here. Okay, did it do this? See my hands? Did it do this? Or did it do this? Did it push it this way? Did it kind of stretch it out to the side? Because that would be kind of a horizontal direction. Or did it take all the points and shrink them down? It took all the y coordinates and shrunk them down. That's why that would be a vertical shrink. Okay? Any questions? Okay, you may have used, if you've seen this before, you may have used the words compression, stretch or compression. Okay? All right. So something that I want you to notice is this. If we think about when we made the change to the shape. So let's take this one right here. What is this going to do to the graph? Up 2. So if I move it up 2, there's the vertex now. We haven't done anything else to the shape. So we could actually graph a whole bunch of points on this by going, we'll go over 1 and up 1 squared. We'll go over 2 and up 2 squared. We'll go back 1 and up 1 squared, back 2 and up 2 squared. So that is the exact same shape. It's just been moved up 2 units. So again, this would be 0, 2. I'd like to label a couple points on here. What would this one right here be? From 0, 0, I went to the right 2. Which coordinate changes if I go to the right 2 units? The x-coordinate does. So this would be 2. 0 plus 2 is 2. And if I went up 4, if I go up 4, which coordinate changes? The y-coordinate does. So if I go up 4, it would be 6. And what would this one right here be? Negative 1, comma, it'd be 3. Okay? Now, how could we make sure that we actually got those right? We could plug them in, couldn't we? Okay? If I plug in a 2, I get 2 squared plus 2. I get 4 plus 2, and that is 6. Does that point on the graph? Absolutely. But we didn't get it by plugging in points. We didn't get it by using an XY table or a calculator. We know that that's the right shape. What does this one do to the graph? Down 1 unit. So that means the vertex is going to be there, and then I'd go over 1 and up 1 squared, over 2 and up 2 squared, back 1 and up 1 squared, back 1 and up 2 squared. So it looks like this. And again, we should be able to label those 5 points. So if you can look at a point and figure out, not by counting, not by looking at it, hey, this is a pretty accurate graph, I can guess where it is, but by doing this. This is 0, negative 1, and if I go to the left 2 units, that's going to be negative 2 for an x-coordinate. If I'm at 0, negative 1, and I go left 2, and then I go up, how far would I go up? Up 4. What's that going to change? The y-coordinate, so that's going to be a negative 2, 3. And again, you could plug it in, you could check in making sure that that works. Okay? This is going to be a vertical stretch. It's not going to move it anywhere. It's going to change how tall the y-coordinates are. It's going to multiply all the y-coordinates by 3. So this is still going to have a y-coordinate of 0. If I go over 1, how far up am I going to go? How far up do I normally go? I normally go up 1, but I times that by 3, so I'm going to go up 3. And I'm going to do that on both sides. Okay, now everybody watch, please. Just watch for a second. The next one, I'd normally go over 2 and up 4. I'm going to go up 3 times as far as 4. 3 times 4 would be 12. That's going to be way up here. And then I'm going to have a point on either side, and I could graph those. Please don't do this. Okay? Don't make it look kind of like a V shape. I mean, as much as you can, you want to round that off just a little bit. I mean, make it look good, and then, of course, put arrows on the ends. Okay? Sven, what does this one do? Flips it upside down. That's what the negative does. Okay, so this is going to open down instead of opening up. Okay, and what does the 2 do? Makes it steeper. Okay, so we're going to make it open down. So we're going to go from the vertex, because we didn't move this left, right, or up or down. We're going to go to the right one, and then we're going to go down. How far? How far? 2. Yep, we're going to go down 2. So that point right there would be 1, -2. I'd normally go to the right 2 and then down 4. I'm going to go right 2 and down, how far? 8. So this next one is 2, -8. And then the cool part about this is there's a lot of symmetry with these. So this point right here would be -1, -2, and this would be -2, -8. So there's our graph. Again, we'd want to round it off just a little bit. And again, as long as we've labeled points, then we're in good shape. Okay, here's what I want you to take a look at. Everybody watching? Made the shape, added 2. That moved it up 2. Made the shape, subtracted 1. That moved it down 1. Made the shape, times it by 3. That vertically stretched it. It made all the points taller. It made the graph steeper. Made the shape, then times it by -2. The negative flips it across the x-axis. It's a reflection across the x-axis, and stretches it out. So this is what we get here. So you'll notice that in every one of these, we made the shape first, then we changed the y-coordinate. Okay? That's why every one of those, if you make the shape and then change it after the fact, it's going to be a vertical change. A shift in these cases, a stretch, a shrink, a vertical flip in those cases there. Okay? Now, this next part, these are different. And this is a little bit harder to understand, and I'm going to ask for an explanation. Maybe somebody can explain why these do what they do. The very first thing that I do here when I plug in a number is I subtract 3 from it. So if I plug in a 2 for an x, the very first thing I do is I change the x that I plugged in, then I square to make the shape. Okay? If I do that here, plug in a 1. The very first thing I do is I add 4 to it before I square to make the shape. Which way is this going to move it? This is going to move it to the right. Okay, and it's going to look, let me blow this up. Okay, it's going to look something like this. Again, over 1, up 1 squared, over 2, up 2 squared. So we should be able to label those points. Back 1, up 1 squared, back 1, up 2 squared. So here's what the graph looks like. This vertex is at 3, 0. Where is this vertex? Okay, -4, 0. But it's the same shape. Again, from the vertex, go left and right 1, go up 1, left and right 2, go up 4. So I get exactly the same shape. It's just been moved left or right. Okay? So whenever you make a change to the x before the function makes the shape, it changes it in a horizontal direction. And it does the opposite of what you think. So you would think that subtracting 3 would move it to the left 3 and adding 4 would move it to the right 4. It doesn't work that way. It does the exact opposite. Okay? Adding moves the graph left, and subtracting moves the graph right. So, can anybody think of a good reason why this moves right and this moves left? I'll take any reason, not even a good reason. Anybody think of why it does that? We're changing the x. We're adding something to it or we're subtracting something to it. So if I subtract 3, you would think it would back it up 3, but it doesn't. It moves it forward 3. It moves it to the right 3. It takes us a little longer to make the shape. It takes us 3 units to the right to make the shape. Anybody want to take a stab at it? Okay, stop and think about this. Okay, if you were really good at doing something and somebody slowed you down, delayed you, it would kind of move you forward in time of getting it done. Like if you normally got done at noon and they slowed you down, it might get you done at 3. So slowing you down moves your completion forward. Does that make sense? What if somebody helps you out and they speed up whatever job you're doing? If you're normally done at noon and they speed it up, you'd get done sooner, wouldn't you? So think of it this way. When you plug in a number, the very first thing we do with it is we subtract 3 from it. We slow it down by 3 units. So where it normally comes down and makes the shape and hits that turning point at 0, subtracting 3 slows it down and it makes it 3 units later than it normally would. Does that make sense? What happens when we add 4 to it? If this slows it down and has it make the shape later than it normally does, what does this do? Yeah, it speeds it up. Okay? It makes the shape sooner, 4 hours sooner than it normally would, or 4 units sooner than it normally would. Does that make sense? Okay? That's why they do the exact opposite of what you'd think. Okay? It's a little bit counterintuitive. Okay? So if I did x plus 3, it speeds it up, so it's going to make the graph 3 units sooner. Or sorry. Yeah, 3 units sooner. There we go. So it's going to make a shape like that. Okay? All right, go ahead and flip the page over. So now we get to do a couple of interesting things. And we'll get as many of these done as we can because we've basically covered all the ideas. And the rest of this is going to be practice using different types of shapes. Okay? If any of this has been confusing, I really, really encourage you to take time to think about why these transformations do what they do and why these shapes make the shapes they do. Okay? So we're going to put all of these together, but notice what shape we've got right here. This is x cubed. So off to the side, I'm going to do this. That's what it looks like. That's what the parent graph looks like. And then let's keep track of what the changes are that we've made here. What does the minus 4 do to the graph? Okay, this is going to be down 4. Hopefully I've got enough room here. What does the plus 1 do? Left 1. And what does the 2 do? Okay, this is a vertical stretch. It's going to make the points taller. It's going to make the y coordinates taller. Okay? So I'm going to take the center here, which is normally a 0, 0, and I'm going to move it to the left 1 and down 4. So left 1 and down 4. So we're going to be right here. Okay? That's that new center point. I normally go to the right 1 and up 1 cubed. Remember, it's the cubing function here. So I'm going to go to the right 1 and up 2. I normally go to the right 2 from that center point, and I go up 2 cubed, so that would be 8. I'm going to go up twice as far, so I'm going to go up 16. So if this is the point -1, -4, if I go over 2, that's going to give me a y coordinate of 1. And if I go up 16, that's going to give me a x coordinate of 1, a y coordinate of 12. Because I'm going to go up 16 from -4. Does that make sense? Doesn't even fit on here. Okay? What if I go to the left 1? Do I go up or down? Okay, we've got this kind of lazy S type shape. We're going to go down just as far as we went up, so we're going to go down to there. So that's going to be -2, -6. This one is 0, -2. So it's going to look something like this. Does that look like this graph up here in the corner, the parent graph? Does it look like it's been moved back 1 and down 4? And then does it look like it's been made steeper or taller? Okay. Any questions? How could you check and see if we got this right? Yeah, plug in a point. Let's see what happens here. If I plug in a 1, I get 1 plus 1, that's 2. 2 cubed is 8, times 2 is 16, minus 4 is 12. Lo and behold, we got it right. Okay? And again, we got it right from the pattern, not from an XY table or plugging in points, okay? Because we understand what the pattern is, okay? Let's take a look at this right here. Again, let's start at the back. What's this going to do? Up 2. What's that going to do? Left 3. And what's the 1/2 going to do? Okay, a vertical shrink, or we could also think of it this way. It's going to make the points half as tall as they used to be. Okay, so here's what I'm going to do. We're going to go, let's see, left 3 and up 2, left 3 and up 2, so we're right here. And again, the parent graph looks like this. Might want to keep in mind that this point would be 1, 1, and the next most convenient point would be 4, 2. So I'm still going to have something that does this, but I'm going to go over 1. Remember, this point is negative 3, comma 2. Over 1. Which coordinate could you tell me right now if I went to the right 1 from this point here? X coordinate would be negative 2, right? I normally go up the square root of 1. Okay, because remember, over 1 up the square root of 1, over 4 up the square root of 4. I'm not going to go up 1. How far am I going to go up? Half as far. Okay, so we're going to be about right there. Make that look a little bit better. Okay, so that would be 5/2. Better to write it as 5/2 than 2.5. Just get used to that. The next most convenient point, I'd have to go over 4. So over 1, 2, 3, 4. I should be able to figure out what my x coordinate is. My x coordinate is 1. And then I would normally go up square root of 4. I'd normally go up 2. I'm not going to go up 2. I'm going to go half as far as 2. So how far up am I going to go? 1. So I'm going to go up 1. So this is going to be 1, 3. And the graph is going to look like this. Okay, now take a good look. Does this graph right here, I mean, it almost looks like a line. It's not. It's not a line, okay? It gets more and more shallow, okay? It's got a curve to it. Does this look like I took the original one that I drew here in red and kind of dotted? Does it look like I moved it back 3 and up 2? And does it look like I took the points and made them shorter, made the graph so it's not as steep? Okay? Any questions? Okay. I want you to take a look at these guys right here. And I want you to see if you can graph those. We're going to pick up right there tomorrow. It won't take the entire time to finish this, but you could get started on the homework, at least to some extent. 1.5 is not assigned, but I'd go ahead and get started on it, okay? Have a great day.